Given a transformation that goes from Rn to Rm, we are going to define a subspace here of the domain that is going to be called the kernel of the transformation. The kernel of the transformation is going to be a subspace here of the domain such that when transformed by t goes to 0, where 0 is the vector 0 in the space Rm. So the kernel of the transformation is the set of all the vectors that get transformed into the vector 0. The range of the transformation, if we have again Rn, Rm, and a transformation T here, is a subspace of the codomain here. So this is the image of T, image or range of T. So the image of the transformation is a space here that comes from something here. The image of the transformation is the set of vectors in the codomain such that they come from some vector in the domain. So the vectors here that they don't have anything in the domain that they are the image of, they are going to be outside of the image of the transformation. So for example, in the transformation that we had before from R3 to R2 that takes an xyz in R3 and transform into x minus y x plus z. So this transformation, what is the kernel of this transformation? Well, according with this definition, the kernel of T is going to be equal to the set of vectors here in the domain, so the x, y, z in R3, such that when we transform them, when we do this, to x minus y x plus z, I obtain the vector 0, 0 in the codomain. So the set of vectors that when transformed, they are 0. And we can calculate what vectors are these by just solving here the system of equations. So we can say that this is the x, y, z in R3 such that 2x minus y is 0 and x plus z is 0, right? So that will have to happen for these two vectors to be the same. And we can solve the system of equations and we can say that the curl is the set of x, y, z in R3 such that, and we can put everything in function of x. For instance, y is equal to 2x and z is equal to x. So if you like, you could also put that in here in the definition of the vectors. In any case, this vector, this kernel, is defined as the vectors in R3 such that the y is equal to 2x and the z is equal to x. So for example, does the vector 3, 6, 3 belongs to the curl? It does, right? Because we have here that the y is double than the x and the z is equal to the x. So yeah, so that one does belong to the kernel. So what about the vector 2, 2, 1? Well, this vector does not belong to the kernel since the y is not equal to the double of the x. That's it. So it doesn't belong to the kernel. Okay, so we have an idea then what is in the kernel of in the kernel of this transformation. In the same way, you can define what is the image that should be a subset of the two-dimensional space. Let's review now two ideas that you already knew about functions, which is injective and surjective functions. So a function is injective. It have to happen that two different inputs cannot go into the same output. So in order to be injective or one-to-one, that is another way to say injective, have to happen that the transformation maps distinct vectors in distinct vectors. So if we have two vectors that are not the same, when you transform them, they cannot become the same. They have to be transformed in different vectors too. And relating this to the associated matrix, we can see that this is actually completely equivalent to the columns of the associated matrix to be linearly independent. This is going to be a very practical condition to check injectivity in a linear transformation. We just can calculate the associated matrix and see if the columns of the matrix are linearly independent. If they are, so then the function is injective. Otherwise, it's not. Surjective, we can say, you also know that a function is surjective with everything in the codomain is the image of something in the domain. So we can say that this transformation is surjective or onto if every vector in Rm, in the codomain, is the image of at least one vector in Rn. So cannot be that there are just elements in the codomain that they don't come from anything. So in order to be surjective, everything has to come from something in the domain. And translating this to the associated matrix, to the transformation, we're going to say that this, to be surjective, is completely equivalent with the columns of the matrix to span Rn. So we have that looking at the matrix associated to the transformation and looking at the columns of this matrix, we can see that if these vectors are linearly independent, so the transformation is injective. And if these vectors span the whole codomain, so then this transformation is surjective. So let's review some results that are going to be very, very useful in practice. So this is a very important result, that the dimensions of the curve plus the dimension of the image is always equal n. Always equal the dimension of the domain. This is a very important equation because considering the dimension of one of the spaces, using this formula, you can always calculate the other one. And here it comes that in the second theorem comes the relation between the curve and the injectivity. So the idea is that being injective is the same thing that saying that the kernel of the transformation is zero. So if the function is not injective, if the function takes several vectors to one particular vector, so then in those cases the kernel of the transformation is going to be bigger. It's not going to be just the zero. So the function is injective if and only if the kernel of the transformation is zero. And in the same way, the function is surjective if and only if the image of the transformation is the whole codomain. And so that, combined with the relation that we have here, we are going to say that to be injective is the same thing that to say that the kernel is zero, and it's the same thing that saying that the rank of the matrix associated to the transformation is n, which is this dimension here. So in the same way, the second part of the result says that the transformation is surjective, is equivalent to say that the image is the whole codomain, and it's the same thing that the rank of the matrix is actually M, this one here. So we have a very practical way to check if something is injective and surjective. And everything boils down to the rank of a matrix. The function is injective if the rank is N. The function is surjective if the rank is M. So this is a very practical condition to know when the function is injective or surjective. So in our particular transformation that was from R3 to R2 that had this particular formula, we had calculated the curve before. So the kernel of this transformation was equal to the x, y, z, such that y was 2x and z was x. So in particular, we can see that in this curve, there are things, right? Things other than 0. In fact, we calculated some vector, like the vector 3, 6, 3, that is in the curve. I mean, it's not only the vector 0, 0, 0, the one that is in this kernel. So we know that this vector is, this kernel is not 0. So because of that, we can say that this transformation then is not injective, right? Because we know that the curve is not 0. Moreover, we can calculate the rank of the associated matrix that we have. The associated matrix to this transformation was this one. So we can see easily that the rank of this matrix here is 2, since we can find here a determinant 2 by 2, for instance. So the rank of this matrix is 2. So we can see that the rank is 2. So this M there. So the rank is M. So because of that, we can say that our transformation is then surjective. So it's not injective, but it's surjective. More in this case, that the dimension of the image, which is the rank, is equal n. N in our case was 3. So we can see now that the dimension of the kernel here have to be 1. Right? So we can deduce from here that the dimension of this curve is 1. So the dimension of this space is 1. So we can see that actually it's a line, right? So in R3, a space of dimension 1 is a line. So we can deduce that. Also, since we know now how the equations of the lines look like, so we could have seen directly that this is actually the equation of a line, right? Given in parametric equations. If a linear transformation is both injective and surjective, so then we are going to say that T is an isomorphism. So T is an isomorphism if T is injective and T is surjective. And we can see that this coincides with the idea of having an inverse transformation. So we can say, as another remark, that T is an isomorphism if and only if T is invertible. T has an inverse. So it's equivalent then to be an isomorphism, to be injective and surjective, is equivalent to be invertible, to have an inverse transformation. Particular case, when the transformation happened to be from Rn to itself, so this condition gives some extra equivalent ones. So if the transformation happened to be from Rn to Rn, so if it's 1 to 1, it's necessarily surjective. If it's to be injective, it's equivalent to be surjective and it's equivalent to be invertible. And there are many other things that I would encourage you to think one by one. Why are those? But it's completely equivalent to the matrix to be invertible, and it's the same thing that if we consider this as a system of equations, right, putting here the matrix associated to the system and here the vector, so this system has only the trivial solution, compatible with only one solution. And also it's equivalent to say that the reduced echelon form of this is actually the identity matrix. And it's the same thing that a system like this with any vector B here has exactly one solution. And it's the same thing that's saying that the determinant of the matrix associated to the transformation is not 0. It's the same thing that the column or the rows are linearly independent or span the space, which is the same thing that saying that is a basis of the space. And it's also equivalent to say that the rank of the matrix is n, and it's also equivalent to the term of the transformation to be 0 and to the image of the transformation to be the whole codomain, right? So this is the same thing to be an injective or surjective. And also will be equivalent to say that the transformation T is an isomorphism.